All right, so welcome back to the Civil FE exam review. Today in this video, we're going to be continuing our geotechnical engineering section of the review, and we're going to be focusing specifically on slope stability. So if you haven't checked out any of the videos leading up to slope stability, definitely check those out. They go into a lot of detail dealing with soil stresses, different types of tests that are in the field, phase relations, classifying soils, bearing capacities, all that stuff are in prior videos. So definitely want you to check those out. All right, so let's look at number one. Number one says an excavated slope is shown below. Okay, determine the length of assumed planar slip surface. Okay, so how do we start this problem, right? See, they give us a depth. See, they give us an angle of 20 degrees, and I see some force coming down. That is 3,036 kilonewtons per meter. So let's write out our given information. They give us the weight of the soil. They also give us the angle. Some sort of angle. Don't know what that angle is. And they give us the height of excavation. Okay, so we need to find the length of assumed planar slip surface. All right, so I'm just gonna look up planar slip surface. Maybe I just need to do slip surface. See if anything comes up. Slip surface, 16s come up, just not too bad. Okay, and they're all looks like on the same page. So this looks like where I need to be. We're in the geotech section. Okay, let's take a look at these. They say that the assumed planar slip surface is here. So it's this line that's angled. And so on our diagram, that same line, let's highlight it so that you know exactly what I'm talking about here. It's that line there, right? So, okay. So if we're wanting to we want to determine the length of that slip surface. Okay, so they give me an angle of the slip surface from the horizontal. They also give me the height, right? So if I have an angle and I have a height, can I use trigonometry to get this? Because they're just saying they want to know the hypotenuse of this triangle, right? We have the height of it. Let's get a right triangle. Okay, so if I have the height, right? So I have the opposite, right? So if I say the sine of 20 degrees should equal the opposite over hypotenuse, right? So the opposite is 15 over the hypotenuse, which is the length of the slope of the slip surface. And it also is denoted here, LS, length of assumed planar slip surface. So I know that I'm doing the right thing now. All right, no question about it. So I can denote this as LS, all right? So LS is equal to 15 over sine 20 degrees, which equals 43.86. And that is in meters. Right? So that's the length. A. So it's 15 high, right? And then this yellow distance, now red distance, is going to be your 15. I mean, it's going to be your 43.86 meters. Okay. Cool. Let's look at number 2. All right. So this one says, what is the mobilized shear force in kilonewtons using the following information? All right. So we have a factor of safety of 1.5 and available shearing resistance, which is equal to 1,000 kilonewtons per meter. We have a length of assumed planar slip surface, which is equal to 30 meters. We have the weight of the soil, which is equal to 500 kilonewtons per meter cubed. All right. How do we get this? Well, we're trying, what are we given? What information are we given? Well, we're given a safety factor. We are also given a shearing resistance, right? SR, shearing resistance. We're given the length of assumed planar slip surface. Length of slip surface. Okay. And we are given the weight of soil. Okay. So we're trying to find the mobilized shear force. So I don't know where to start, so I'm going to search mobilized. Only one thing for mobilized. All right. So mobilized shear force, T stands for T-mob, or its symbol is T-mob. So what is T-mob on this diagram? So T-mob is the force coming down, or it's the mobilized shear force along the slip surface. So what can be moving, right? All right. So T-mob is equal to WM sine whatever that is of S. So what is A sub S? It's the angle of assumed slip surface with respect to the horizontal. Okay. So do we have that? No. Okay. All right. So is there any way else we could get T-mob? Well, we have factor of safety, right? Factor of safety equals TFF over T-mob. Can we get, we have factor of safety. Can we get TFF? If we can get TFF, then we can solve for T-mob. So TFF is equal to C. What would C be? What is TFF? It's the available shearing resistance along the slip force. Wait a minute. We already have that. That is available shearing resistance here. We have that, so we can literally solve for this. It's not as hard as I thought it was going to be. So we know that factor of safety is equal to, they gave us a bunch of variables that we did not need. Had me thinking I was going to have to work way harder. Okay, so factor of safety is equal to TFF over T mob, right? And we are trying to find T mob, right? All right, so T mob is equal to TFF. I'm just moving it around so that I can just plug and be done. So what is TFF? TFF is 1,000 kilonewtons per meter divided by the safety factor of 1.5. So when I solve for this, get T mob is equal to 667 kilonewtons per meter. So if I want to make sure this answers in kilonewtons, right? So I want the force to be in, so we could say is 667 kilonewtons per meter, but it goes for a distance, and that's where it goes for a distance of 30 meters. So I'm going to multiply this over a distance times 30 meters. And that's going to cancel out our units. And so I get this to equal roughly 20,000 kilonewtons, or B. Right. All right. Let's get number 3. All right. So using the following information, determine the factor of safety against sliding. Okay. Angle of internal friction is 30 degrees. Cohesion is 19.2 kilopascals. Weight of soil above the slip surface is 3,036 kilonewtons per meter. And the length of the slip surface is equal to 44 meters. All right, where do I start? I start by, first of all, writing out my given information. So my given information is all here, right? So up above, they do a pretty good job of laying it out, so I'm not going to rewrite everything that's already been written. What are we trying to find? We're trying to find the factor of safety. Against sliding. Okay. So what formulas might I need for this? Well, I feel like I'm already in the right area, but if I was not, let's say I wasn't in the right area from the last problem that we did, I would probably search sliding maybe. See what comes up there. Okay, so this is for retaining walls. So I don't think I would use these. Okay, so none of those. So that wouldn't get me anywhere. Maybe slip surface. I see length of slip surface and I see above slip surface, so maybe slip surface. So 6 things come up, and when I search slip surface, it brings me to like slope stability and a place where I see factor of safety against slope instability. So very similar for what I'm trying to solve. So I know that I'm trying to solve for the factor of safety here, FS. I'm looking for FS. All right, so how do I get my FS? Well, I know that FS, start by saying FS is equal to TF F and T mob. Okay, so I just copied what I'm seeing here. All right, what else? Do I know TFF? Well, can I get it? Do I have C? I have cohesion, LS. LS is the length of the assumed planar slip surface, so I have LS. What about WM? It's the weight of the soil above slip surface. I have that at 3,036 kilonewtons per meter. Okay. Do I have this angle of assumed slope surface? Don't know if I do. So, 30 degrees slotting. I don't believe that I do. So what I would do, just gonna plug a random, or can we solve for it? Angle. Maybe we need to solve for that. Okay, so this is throwing me off a little bit. So maybe we need to start by solving for T-mob. Okay, and then if I have T-mob, I'll know what angle angle S is. Okay. Angle assumed slip surface. Okay. So, T-mob. What is T-mob? T-mob is the mobilized shear force. So, weight. You have the weight of the soil above the slip surface. And you still need the angle of assumed slip surface. So I don't believe we have enough to solve this particular problem. So what I'm gonna do is I'm going to add something to this. I'll say the angle of assumed slip surface is equal to, we'll just say 20 degrees. So if it's 20 degrees, right, then we would have all the variables necessary to solve for TFF and TMOB. So let's do that. So if I have that information now, I would know that TFF is equal to, what's my C? 19.2 times my 44 meters times, or plus, WM, which is going to be 3,036 kilonewtons per meter. Okay. Times my cosine of 20 degrees times the tan of phi, which is the angle of internal friction, which is 30 degrees. All right, and so when I solve for TFF, I get that to equal 2483.12 kilonewtons per meter. All right, and so now we have TFF, we just need TMOB. TMOB would equal to our WM which is 3,036 kilonewtons per meter. And then what else are we need? Oh, sine times the sine of 20 degrees. So TMOB is equal to 1,038.37 kilonewtons per meter. All right, so now we know FS, our safety factor, is going to be equal to 2483 kilonewtons per meter over 1038.37 kilonewtons per meter. And this is just roughly. This is going to equal to 2.39 or 2.4 for the safety factor. Let's see. All right. So it'd been nice if I would have included that variable into this question, but basically the gist of it is to take the information that you're given and be able to solve for your unknowns, right? So this concludes the slope stability section for the geotechnical engineering review. In the next video, we're going to be finishing up the geotech section with soil stabilization. So we'll see you in the next video.